Okay, so students, we're into the next unit. We're going to be talking about elements and their electrons. We're going to be looking at orbital diagrams, electron configurations. We're going to be talking about what are valence and coherent electrons, and then we're going to look at the periodic table and kind of sum up and look at the different trends we can take away from that particular periodic table. So some of the topics we're going to be talking about in this particular unit is we're going to talk about what are shells and subshells. We're going to determine how to draw orbital diagrams. We're going to look at our orbital diagrams and come up with electron configurations. From the electron configurations, I can determine what my core and valence electrons are. I will then also be able to write noble gas configurations. And lastly, like I said, we're going to talk about some periodic trends. By looking at the periodic table, we'll be able to come up with a few trends that we'll be able to follow. I'd like to start off by talking about, can we see an electron? So as you're going through this chapter, okay, you're going to see these different colors and so forth. As our eyes are able to see what we call visible light. So when we look at the electromagnetic spectrum, okay, and this is kind of the physics of chemistry, but as we look at the electromagnetic spectrum, there's some sort of wave associated with it. Now, this very small part of the electromagnetic spectrum is what we call visible light. Red all the way to violet. I learned it as Roy G. Biv. These are the colors that we are able to detect with our naked eye. Now, we can't detect radio waves or X-rays. We can't see those waves coming at us. When I worked in nuclear chemistry, we had to wear certain badges and so forth. That way that we could be detected whether we got hit with the nuclear radiation or not. So I guess what I'm saying is can we see an electron? No, we cannot. All right, but the fascinating part about it is when we add electricity to an electron, it will actually move or vibrate in such a frequency that we are able to see different colored lights from it. And so if we look at the top spectrum here, we see that the white light spectrum, the Roy G. Biv, all sorts of colors there. If I look at the hydrogen light spectrum, notice how I have a few colors in the hydrogen light spectrum. The helium light spectrum, there's a few more colors. As I add energy, I can change the color of that particular, the output of that particular electron. As it traveling around the nucleus of the atom. I want to call your attention to the last one here, the neon light spectrum. Okay, notice the various shades and colors. Okay, it's kind of interesting. I tell my students, why do you think they make so many what we call neon lights, right? Many businesses use these different colors and so forth to show you that they're open, or maybe a cute little sign on the wall. Neon, very interestingly enough, at different levels of electricity that we apply to it, we can change the wavelength of those, and we get these very unique emission spectras of various shapes and colors. So to start off, the Niels board developed a simple model for these particular atoms. Okay, and we talked about the nucleus. The nucleus of an atom, right, is the small dense core. And then these electrons travel around the outside of the nucleus, traveling in different energy levels. N equals 1, N equals 2, N equals 3, 4, 5, and so forth. So the electrons get further away from the nucleus as it goes out. This representation of the ladder, okay, at the N equals 1 level, it takes so much energy to climb from N equals 1 to N equals 2. Now, the reason I show you this ladder is there's a lot more energy to jump from the first energy level to the second energy level. And what happens as we go from the second energy level to the third energy level? It takes so much energy and so forth. So it takes more energy for these electrons to move up this particular ladder. Now, something that you may be familiar with and things you've seen as a child or so forth is the glow in the dark, right? Those sulfide compounds that are glow in the dark. They take in the light from your room, and then when you turn the lights off, they re-emit those back. Well, what's happening is there's certain compounds that when we add light to them, their electrons become excited. So what happens is they jump up to the next energy level. Then when we shut the lights off in our room, what happens is that light is re-emitted from that particular compound so that we can see it. When we wake up in the morning, okay, whether that dial was on our alarm clock, whether it was a certain poster we had or so forth, when we wake up in the morning, that light is no longer, or that reflection, or glow in the dark, as we refer to it as, is no longer there. And why is that? That is because as the night progresses, it falls from the energy level, say n equals 3 down to n equals 2. And what we call, and you will come to be familiar with this, what we call the ground state of a particular electron. These particular levels that the electrons are from the nucleus of the atom are what we call the quantum levels. Quantum levels. They are n equals 1, 2, 3, all the way up to n equals 7. So there are 7 quantum levels, or there are 7 principal shells or levels that we can be from the nucleus of an atom. What I want you to take away from this, okay, we've talked earlier in this semester about the rows, or the columns on the periodic table. The alkali metals, alkali earth metals, halogens, noble gases, things of that sort. When we're talking about quantum levels, I want you to look at the rows going across, okay? And what we'll find out as we're going through this particular chapter, elements in the first period, n equals 1, has quantum levels of 1. In the n equal 2, we have an energy level that goes into the second quantum energy level. In the third period on the periodic table, or row, is the third quantum level. Okay, so this will help you when you're doing your activities to see what energy level or how far away am I from the nucleus of the atom. I can simply look at a periodic table and determine what the energy level that will be in. For example, if I look up where is magnesium, right? Here's magnesium on my periodic table. It is in the n equals 3. So that tells me that the electrons are going to be out here in the third energy level, the third ring from the center of the nucleus of my atom. It's just kind of a quick way to double check to make sure you're on the right track. Now, what happens to the energy? The energy increases as we go down the periodic table. So in other words, the more electrons we get, right, the more energy it takes. I want to talk about the subshells. Okay, we just talked about the quantum levels. Those are the 7 principal shells. Now I want to talk about the shapes of the quantum mechanical orbitals. The shapes are specific by what we call the subshells. We have an S, a P, a D, and an F. Okay, so here's kind of a representation of what's happening. Now, this particular chapter, right, there's not a lot of mathematics involved in it, a lot of notation. This is the physics of what's going on. So when we think about chemistry and chemical reactions and atoms bonding with one another, okay, these particular atoms actually never touch one another. What happens is the force between the atoms is holding them together. And the force that's holding them together is because of these particular shapes and how the electrons are traveling. Okay, so you're not going to need to know these different types of quantum mechanical orbital shapes and so forth. But the things I do want you to know, that let's start off with, we have the S, we have the P's, we have the D's, and we have the F's. So there are 4 subshells, SP, D's, and F's. With the S subshell, so the S subshell has 1 pair of electrons or 2 electrons. In the P's, the P has 3 pairs of electrons or 6 electrons total. In the D has 5 pairs of electrons meaning it has 10 electrons. And in the F subshell, I have 7 pairs of electrons or 14 electrons. So there are 4 subshells, an S, a P, a D, and an F. The S has 1 pair of electron. The P has 3 pairs, the D has 5, and the F has 7. Now, you will also hear the pair of electron referred to as the orbitals. How many orbitals do I have going around the nucleus of my atom? In the number of subshells in any given principal shell, okay, and I know a lot of this is definition type stuff. I'm just trying to give you a background so when we start doing these orbital diagrams, you'll kind of see where I'm getting these from. In the principal shell, n equals 4, we have 4 subshells. We have the S, the P, the D, and the F. So in the 4th energy level, from the nucleus of my atom, I have 4 subshells. In the 3rd energy level, or 3rd quantum level, I have 3 subshells. I have the S, the P, and the D. In the 2nd energy level, I have 2 subshells, known as the S and the P. And lastly, in the n equals 1, or the 1st energy level, I have only 1 subshell, and that is the S. Okay, now this is what we'll come to find as a standard. Okay, so in the 1st energy level, or 1st quantum level, we will have 1 subshell. In the 2nd energy level, or quantum level, we will have 2 subshells. In the 3rd energy level, we will have 3 subshells, and in the 4th energy level, we will have 4 subshells. Okay, and as we progress more, we'll find that in the 5th energy level, we'll have 4 subshells, and then we go back to 3 again. Okay, but for the questions I'm going to ask you, you're going to need to know. If I ask you, what is the lowest, what is the lowest principal shell that a d orbital can be present in? What is the lowest principal shell, the lowest shell that a d orbital can be present in. So I'm asking you, what shell do we find a d orbital, the lowest? Okay, so I see a d orbital is in the n equals 3 and 4, but the lowest one that it can be is n equals 3. What's the lowest one that can contain a p orbital? That would be the n equals 2. So if you'll follow along with me here, over on the right hand side, I have this little picture. Okay, kind of give you an idea what's happening. Okay, so at the first energy level, at the n equals 1, I have how many subshells? I only have one subshell. So that means I'm only going to have one place that is going to be rotating around. In the n equals 2, the next energy level, n equals 2, I have two subshells, the s and the p. So that's why we have these two lines being represented going around that particular nucleus. In the n equals 3, how many subshells do I have? I have 3 subshells. They are the s, the p, and the d. And in the n equals 4, I have 4 subshells, the s, the p, the d, and the f. Okay, now I know a lot of this, you're probably asking, what does all this mean? And we're going to get to it here when we talk about these electron configurations and so forth. So we're going to be relating principal quantum numbers to their particular subshells. Okay, so in the n equals 4 principal quantum number shell, we must have the s, the p, the d, and the f. Okay, so when I'm looking at the first one here, n equals 4, we have the s, the p, the d, and the f. So when I draw an orbital diagram for the 4th energy level, okay, I am going to need an s, a p, a d, and an f. Now, you're asking, well, what's all these boxes and so forth? Okay, each box represents an orbital or a pair of electrons. So the s has one pair of electrons, so we only see one box there. The p has 3 orbitals or 6 electrons, that's why we see 3 boxes. The d has 5 orbitals or 10 electrons, that's why we see 5 boxes. And the f has 7 orbitals or 14 electrons. Okay, so that's why we see 7 boxes there. Now, what about the n equals 3? In the n equals 3, there's an s, a p, and a d. Since we only have the s, the p, and the d, the s contains how many electrons? 2 electrons or 1 pair. So I've got an s. I also have a p. I have a 3p. The p contains 6 electrons or 3 pairs, and the d contains 5. Now let's look at the n equals 2. In the n equals 2, I have an s and I have a p. The s contains 1 pair of electrons. The p contains 3 pairs. Okay, so as I'm looking at drawing my orbital diagram, this is how I will represent it. And at the n equals 1 principal energy level, I only have one subshell, and that is the s. Right? So when I'm writing this one, this is going to be I'm only going to have one subshell. Okay? So the idea of this concept, this is known as orbital diagrams. And we put the arrows in a box, so to speak. We show the signs of those electrons. So what I want to do is I want to talk about writing orbital diagrams and the ground state electron configurations for some particular types of atoms that we find off the periodic table. So, what I want you to note is, looking at your periodic table, I want you to see that lithium is in what period on the periodic table. Period, I'm meaning the rows down. So if I'm looking at my periodic table, and this is just a rough drawing here, I find lithium. Lithium is in the second period down. Because it's in the second period, I only need to go to the second energy level. Okay, so I need to go through the first energy level and then to the second energy level. If I look at nitrogen, nitrogen is in the second period. Oxygen is in the second period. But phosphorus is in the third period. Okay, so in this case, can I use this diagram? For phosphorus, I should have a 3s and a 3p and a 3d. Okay, so I would need more boxes out here because I am in the third period. I would need a 3s, the 3p, and the 3d. Okay, so what I want you to get from this, looking at the periodic table, this will tell you how far out you need to go on these particular ones. Okay, so we can't do phosphorus because we need to go all the way up to the third energy level. Okay, so what we're going to do is we're going to look at the top three here: lithium, nitrogen, and oxygen. Okay, so the first thing you're going to do is find the number of electrons. How do I find that? Well, I identify lithium on the periodic table, and I see lithium is atomic number 3, 6.94. It's its atomic mass. What does the atomic number tell me? The atomic number tells me the number of protons in my particular atom. In the neutral state for an atom, if it has 3 protons, then it has to have the exact same amount of electrons. So in our case, I'm going to have 3 electrons. So lithium has 3 electrons. What about nitrogen? I look up nitrogen on the periodic table. Nitrogen is atomic number 7, so that means it has 7 protons. So that means it's going to have 7 electrons. Oxygen is number 8 on the periodic table, atomic number. That means it has 8 protons. If I have 8 protons, then I'm going to have 8 electrons. So oxygen has 8 electrons. So what we're going to do is we're going to determine what the orbital diagram is for each one of these. We've already established that they are all in period 2, except for phosphorus, which is in period 3. Right? Because it's in period 3, we need more boxes. Okay, so we can't quite solve that one quite yet. So looking at lithium, lithium has 3 electrons. So what I'm going to do is I'm going to count the number of electrons that I have going across. So every square is an orbital, or a pair of electrons. So each square will contain 2 electrons. So watch me do the first one. If I ask you for the orbital diagram of lithium, okay, you're going to draw one half arrow up and one half arrow down. Okay, and why do we do that? That is because one electron is going one way around the atom, and the other electron is going the other way around the atom. If they were to both go in the same direction, right, we wouldn't have equal and opposite forces. So then we would create momentum and inertia, and we'd have a force associated with that. So we have to have equal and opposite charges, equal and opposite forces. So one half arrow up and one half arrow down. Each half arrow represents an electron. So I need 3 electrons. I have how many? 2. So I need one more electron. So I'm going to draw one here in the S. So if I was to ask you to draw me the orbital diagram for lithium, this is what you would give me. If I asked you for the ground state electron configuration, okay, I would write that as 1s2, 2s1, meaning I have 2 electrons in the 1s and 1 electron in the 2s. Let's try the next one. Let's look at nitrogen. Nitrogen has 7 electrons. 1, 2, 3, 4. Okay, so this is our first time for us to travel into a P subshell. And S has only one orbital, 2 electrons. So it's just up, down, up, down. When we get to a P, the rules are we must fill all the up arrows first and then go back and pair up. Okay? So let's look at this one. I need 7 electrons. I have 4. So I have 1, 2, 3, 4, 5, 6, 7. Okay? Draw all the up arrows first. So if I asked you on the test to give me the orbital diagram for nitrogen, this is what it would look like. The ground state electron configuration would be 1s2, 2s2, 2p3. I have 3 electrons in the p. Now, if you want to kind of double check to make sure that you're doing it correctly, so to speak, add up the subscripts. 2 plus 2 is 4, 4 and 3 is 7, 7 is the atomic number of nitrogen. That tells me the number of electrons that I have. Hey, let's look at oxygen. Oxygen is number 8. Okay, so oxygen is number 8. I am going to count 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So my ground state electron configuration would be 1s2, 2s2, 2p4. 2 plus 2 is 4, 4 and 4 is 8. Atomic number 8 gives me oxygen, so I know my electron configuration is correct. Now, let's kind of take a look at this last one here, right? This phosphorus. So let's look at the phosphorus. Now, what I'm going to do is I'm just going to roughly draw these in here. So I've got 3s and 3p. 3s and 3p. And we know that phosphorus, right, is in the 3rd period. So I'm going to have to go out to the 3rd energy level. Phosphorus is atomic number 15. That means I need 15 electrons. So let's start out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if I was to ask you what the orbital diagram for phosphorus was, this would be your correct answer. What is the ground state electron configuration? 1s2, 2s2, 2p6, 3s2, 3p3. And I apologize, it's kind of curving down there at the end. If I was to add all these up, 2 and 2 is 4, 4 and 6 is 10, 10 and 2 is 12, 12 and 3 is 15. Atomic number 15 is phosphorus. Okay. Orbital diagrams refer to putting arrows in a box. Electron configurations are shorthand notation using subscript or superscripts to tell me the number of electrons that I have in each energy level. Now I want to talk about core and valence electrons. So which are my core electrons and which ones are my valence electrons? By definition, my valence electrons are the electrons in the outermost energy level. The electrons in the outermost energy level. Outermost energy level meaning the outermost quantum level. Okay, so let's look at lithium. Lithium is in the second period. What do we expect the highest energy level to be, or quantum level? The n equals 2. So I'm going to look at the 2 for my valence electrons and the 1 for my core. So how many valence electrons does lithium have? Lithium has 1 valence electron. Moving along, let's look at the nitrogen. Okay, again, nitrogen is in the second period on the periodic table, so it is in the second energy level. Second energy level, that is my highest energy level, but in this case I have the 2s and the 2p, leaving the 1s to be my core electrons. How many valence electrons do I have? 2 plus 3 is 5. I have 5 valence electrons. Let's look at my oxygen. Highest energy level is the second energy level. It's in the second period. 2 plus 4 is how many valence electrons do I have? I have 6 valence electrons. Let's look at my phosphorus, right? I'm going out to the third energy level. I'm in the third period on the periodic table. In other words, I'm in the third row down. Where are my valence electrons? My valence electrons are in the third energy level. Okay, all the way out here. Everything else then becomes the core. So I have 10 core electrons, and how many valence electrons in phosphorus? 2 plus 3 is 5 valence electrons. So I have 5 valence electrons in my phosphorus. Now, what you're going to find, uniquely enough, okay, 1 valence electron, lithium resides in what? In group 1A on the periodic table. So is it a coincidence that everything in group 1A will have 1 valence electron? Likewise, Nitrogen has 5 valence electrons. Nitrogen resides in group 5A on the periodic table, meaning that it has 5 valence electrons for each of the elements in that family. Now oxygen, right beside nitrogen, how many valence electrons does it have? It has 6. What did we learn back when we were talking about the periodic table? Oxygen is in group 6A. Why is it called 6A? Because it has 6 valence electrons. Nitrogen, like phosphorus, has 5 valence electrons. So phosphorus also resides in group 5A. What's different about phosphorus than is nitrogen? Phosphorus is in the 3rd period, right? So since it's in the 3rd period, it's the next period down. But it still has the same number of valence electrons as that of everything else in 5A. For example, like nitrogen and arsenic and so forth. Okay, let's look at orbital diagrams and ground state electron configurations. Let's look at magnesium. Okay, now magnesium on the periodic table is in the 3rd period. What does that mean? When you're writing your orbital diagrams, you're going to repeat these over and over again. So you're going to have 1s, 2s, 2p, 3s, 3p, 3d. Okay, so we're going to have to go out to the 3rd energy level. We find the number of electrons that magnesium has. Magnesium is atomic number 12, right? Atomic number 12. So number 12 is going to have 12 electrons. Sulfur is element number 16 on the periodic table, so it is going to have 16 electrons. So what we're going to do is we're going to count across and determine what the orbital diagram is for each one of these. So I need 12. So magnesium, going to have 1, 2, 3, 4. I'm to the P now. I got to do all the up arrows first. 5, 6, 7, 8, 9, 10, 11, 12. Now notice I didn't use the 3P or the 3D, right? So not necessarily are we going to use all of them, but I did stop in the 3rd energy level. My electron configuration is going to be 1s2, 2s2, 2p6, 3s2. Sulfur is 16, so we need 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so that would be the orbital diagram for sulfur. Its electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p4. Now, where does my valence electrons? How many valence electrons does magnesium have? Magnesium, the highest energy level is 3. So I have 2 valence electrons. What group does magnesium reside in? It resides in group 2A. So I have 2 valence electrons. It is in group 2A. How many valence electrons do I have in my sulfur. 2 plus 4 is 6. I have 6 valence electrons with my sulfur that resides in group 6A. So if I was to ask you, what is the ground state electron configuration? You could easily write that with the superscripts. If I was to ask you what is the orbital diagram for these particular elements, you could simply write those out using the arrows in a box. If I was to ask you how many valence electrons that sulfur has, you could add them up. 2 and 4 would tell me I have 6. Same way for magnesium, I have 2. Now, as the atoms get larger, we find that the correct order for filling these orbital diagrams and writing the electron configurations are in such a way. So in other words, when I'm writing or filling these, I must fill the 1s first, then the 2s, travel back up, then the 2p and the 3s. Then after I get the 3s filled, I filled the 3p. This is where it starts to get tricky. Once I fill the 3p, then I go to the 4s. Once I get the 4s filled, then I go back to the 3d, fill the 4p and the 5s, and so forth. Okay? So it's going to be very helpful and beneficial for you to use this particular chart in order to know how to count the orbitals as these atoms get larger. Another concept, or another thing, was use this diagram here. So we go from 1s to 2s, from 2s to 2p, from 2p to 3s, from 3s to 3p, from 3p to 4s, from 4s 3d, from 3d 4p, 4p 5s, and so forth. Okay? Now, when we're writing these electron configurations, okay, when we get to these D's, okay, these D's are going to be in between the next energy level. So what do I mean by that? Look at this one here. Look how the 3D resides in between the 4s and the 4p. Where does the 4d reside? The 4d resides in between the 5s and the 5p. So what you'll come to see is that as we do these problems, the d's are always going to be 1 unit behind the principal shell. So in other words, it'll go 4s, 3d, 4p, 5s, 4d, 5p. Those types of things, okay? So you're always going to see the D's, the principal energy level is going to be 1 unit behind. So, the proper order for filling these particular shells, as we said, what I'm going to do is I'm going to fill the 1s first. Okay, so when I fill the 1s, I simply fill the 1s down here. After I get the 1s filled, then I'm going to fill the 2s. So then I will fill this block. Once I get the 2s filled, then I move on to my next order of operation, which is the 2p. So then I will fill these 3 boxes here. What happens when I get done with the 2p? I fill the 3s. Okay, so then I move down and I fill this 3s. Follow the line back up. I then follow the 3p. Okay, I'm going to do my 3p. And then this is where it gets a little tricky. Okay, so what I like to do is, if it helps out, I tell my students, go ahead and number it at the bottom. Right, so this is the first one. This is the second one. This is the third one you fill. Fourth one, fifth one. Now, notice when I get to that 3p, this is when things start changing. Once I get the 3p filled, I'm going to fill the 6s. Okay, or the 4s, excuse me. That's my sixth step. I'm going to fill the 4s. Once I get the 4s filled, then what's going to happen? I'm going to fill the 3d. So I'm going to come back up here and do the 3d. Once I get the 3d filled, then I move back to the 4p. Once I get the 4p filled, then I move to the 5s. Once I get the 5s, then I move to the 4d. So 5s, 4d. After the 4d, I move to the 5p. The 5p, I go to the 6s. After I do the 6s, then I go back to the 4f. I fill the 4f, the 13. Then after the 4f, I do the 5d. After I do the 5d, I'm going to do the 6p. Okay? And then after 6p, we do the 7s. Okay, so we have to fill them in this order. And what we'll come to see is that there's a particular order that these subshells reside on the periodic table. Okay, so you need to use these particular orders when you're filling. Okay, so let's try an example. Let's do iron. Iron is atomic number 26 on the periodic table. Number 26 means that it has 26 electrons. So I have 26 electrons that I need to count. Now, remember, I can go all the way up to the 3p before I need to start doing this shuffling around. So let's do 26 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now what happens when I get the 3p filled? I then move on to the 4s. Okay? I then move on to the 4s. I had 18 electrons, 19, 20. Now what am I going to do? When I get the 4s, I now go back to the 3d. Okay, so I have 20, I need 26. Fill all the up arrows first. 21, 22, 23, 24, 25, 26. This is the orbital diagram for iron. The electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. How do I get the subscripts? Those are the number of electrons that I have in each of the boxes. If I was to add these up, 2 and 2 is 4, 4 and 6 is 10, 10 and 2 is 12, 12 and 6 is 18, 18 and 2 is 20, and 20, oh, excuse me. So yeah, I made a mistake here. We want to, I didn't have 10, probably, I have how many in the D? I have 1, 2, 3, 4, 5, 6. 3D 10. Okay, so I have 10 in the D. Or excuse me, 6 in the D. I don't know why I keep wanting to put 10 in there. So if I add these up again, I apologize. Add up my superscripts. I have 2 plus 2 is 4, 4 and 6 is 10, 10 and 2 is 12, 12 and 6 is 18, 18 and 2 is 20, 20 and 6 is 26. Element number 26 is iron. That is the correct element. Now I'm asking what is my core and what is my valence electrons. Okay. My valence electrons are the electrons in the outermost energy level. Okay. In our case, what is the outermost energy level? The outermost energy level is the 4s. Okay. So I have 4s. How many valence electrons does iron have? It has 2 valence electrons. Okay, and this is what happens. It starts jumping back and forth in the d, and that's what gives us those variable charges that we talked about. Okay. Let's try another example. Let's do element number 50, which is tin. Tin is element number 50, so that means it has 50 electrons. Okay, so it has 50 electrons. I need to count 50 electrons on my electron diagram. What I also want you to take a look at is tin. What period does tin reside in? Tin resides in period number 5. Okay? What you're going to have to do is you're going to have to use your diagram to figure out which ones we're going to fill. So, which ones do we fill first? We're going to fill the 1s, then the 2s, then the 2p. Once I get the 2p filled, I'm going to fill the 3s, then the 3p. And this is where it gets a little tricky. Once I fill the 3p, then I'm going to come down here and fill the 4s. Once I fill the 4s, I go back to the 3d. Once I get the 3d filled, then I go back to the 4p. Once I get the 4p filled, then I go to the 5s. Once I get the 5s filled, then I go to the 4d. Once I get the 4d, I go to the 5p. Once I do the 5p, then I go to the 6s. We're not in the 6th energy level. Okay, so at this point, we have enough orbitals to fill. I'm going to do 50. Okay, so count along with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Okay, so I have 50 electrons. If I was to go back and ask you what the orbital diagram for this looks like, this would be the correct representation. Now, if I was to ask you for the electron configuration, that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p to the second. Again, if I add all those up, I should come up to 50. Okay? In this case, how many valence electrons does my tin have? How many valence electrons? Highest energy level is the 5, fifth period. 2 plus 2 is 4 valence electrons. Okay, so they're really no different than the smaller ones. The only thing is as they go up the scale, right, we have to kind of juggle which energy level they go into. Now you may ask yourself, why do we have to juggle these energy levels that we're going into? And as we look at this periodic table, we have blocks on the periodic table. We have ones known as the S block, the D block, the P block, and the F block. Okay? Now, you may ask yourself, why don't we have any in the Fs? Okay, these are those lanthanides and actinides that are at the bottom, right? That's this F block right here. Okay, that's where the Fs reside. The D blocks, okay, they're always one behind, right? We talked about those in the period. The D block are the transition elements. The S block and the P block are part of my periodic law on my periodic table. So this is just kind of a rough representation. We've got the 1s, the 2s, the 3s. When I get to the 4s, I then do the 3d, 4p, 5s, 4d, and so forth. Okay, notice how the d's are always one unit behind. Now I want to talk about noble gas configurations. The noble gases we know are elements that are in group 8A on the periodic table. They're the ones that are to the extremely right-hand column, and they are the ones that we say are primarily inert with one another. So, for my noble gases, I have helium, I have neon, I have argon, krypton, xenon, and radon. Radon. Now, helium has 2 electrons. So the ground state electron configuration of helium is going to be 1s2. The ground state electron configuration for neon has 10 elements, is 1s, or electrons, 1s2, 2s2, 2p6. The electron configuration for argon is 1s2, 2s2, 2p6, 3s2, 3p6. Krypton would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now, what's happening here, okay, as we're going through the electron configurations, is these noble gases have a set number of electrons. Helium is 2, neon is 10, argon is 18, krypton is 36. Okay? And these are repeated ones that we see over and over again. So what I tend to do, or what we tend to do, is we tend to replace these electrons, the 1s2, with, in brackets, I will put helium. I will replace the 1s2, 2s2, 2p6 in brackets with the noble gas neon. And likewise, argon and krypton. Now, as you can see, these work really well when I get to very large elements. Like, for example, the one we did where it was 10, right? Element number 50. So when I did 10, it would have been easier than writing that 1s2, 2s2, 2p6, 3s2 to just put in brackets, right, that krypton. That would have helped me take care of a large portion of those electron configurations. So when we're looking at writing electron configurations, specifically noble gas, they're based on the position they are on the periodic table. Okay, so if I was to ask you, what is the noble gas configuration for phosphorus? Okay, now we did this one way back, right? Remember us doing this one early on? So if you need to, go back and look at your notes. What you do is you look for the previous noble gas configuration, which is neon. Neon is 1s2, 2s2, 2p6. If I looked at phosphorus, phosphorus would be 1s2, 2s2, 2p6, 3s2, 3p3. Okay? What am I going to do? We're looking for, to write this in noble gas configuration, I am going to want to replace the 1s2, 2s2, 2p6 in this part of the electron configuration with what? Neon. So I would write that as neon in brackets 3s2, 3p3. It's kind of a shorthand notation for this particular element, right? See how it gets rid of those 10 electrons? Kind of keeps it in a short, concise notation. So here's another example of a periodic table that you might come across where they actually have the configurations right in the squares. And this kind of helps you when they're asking you to determine the electron configuration based off of a noble gas. So in this case, if they were asking you for example, like what is the electron configuration for copper using the noble gas notation, what we end up doing is we'll go back and we'll look at the previous noble gas before copper. Okay, so if this is, I'm looking for what is the noble gas configuration for copper, what I would do is go back to the previous noble gas. Okay, so since copper is 29, I can't pick 36, I'm going to pick 18, which is argon. So I would write that as argon in brackets, Ar, 4s1, 3d, 10. I could also say we pick another one. For example, let's say I picked arsenic. Okay, if I picked arsenic, I would have Ar being my noble gas, those first 18 electrons, 4s2, 3d10, 4p3. Okay, so sometimes, and if you come across these, they make it writing the electron configurations a lot easier by having those subscripts in there. But you kind of got to know which ones are the D's and so forth, so when you're filling these up, that you get them correct. The last thing we want to talk about are these trends on the periodic table. Okay, and we can look at the periodic table to determine whether an atom will increase or decrease in size based off of where it's placed on the periodic table. And I'm sure you've all heard of everything is relative to the hydrogen atom. Okay, so hydrogen is number 1 up in the top left-hand corner, and everything is relative to it. Its atomic mass is roughly 1, so the rest of the masses are taken from that hydrogen. When we're looking at atomic size, so atomic size, I find that atomic size increases as I go down the periodic table, and it increases as I go from right to left on the periodic table. So in other words, the atoms get larger as I go to the corner. So radium, francium, barium, those ones are very large atoms in size. We also, another trend look for on the periodic table is metallic character. Metallic character follows the same trends as atomic size, right? Which should be no surprise to us, right? We remember when we talked about early on metals, nonmetals, and metalloids, right? We talked about this stair-step case that goes down in between them. These are my nonmetals. These are my metals. And the ones that touch the line, except for those exceptions, are what we call metalloids. So if I look at my periodic table and I'm determining which ones are most metal-like, those are going to be the ones that are on the metals on the periodic table. Okay, so what's more metal-like is going to be increased as we go down and increased from right to left. The last trend we're going to talk about is ionization energy. Okay, now metallic character and atomic size, they follow the same trend, right? Now, when I look at ionization energy increases from left to right and from bottom to top. Okay, so ionization energy increases from left to right and from bottom to top. So what becomes the highest electronegative element? Okay, in our case, it is fluorine. Right? Remember, those noble gases, they're primarily inert, so they're not going to react with anything. So, if we look at HF, very interesting compound, hydrofluoric acid, ionization energy. It has the ability, HF, to etch glass. Okay, it has a very high ionization energy, and because of that, it's able to etch glass. And we think about glass and how tough it is. We use glass, Brasillite glass, for beakers and so forth, right? But remember, HF has the ability to actually etch that glass or make it like frosted. So when we're looking at this, you will be asked questions like to compare things on the periodic table. Which element is larger than the other one? Which element has more ionization energy than the other one? Which one has more metallic character than the other one? Let's look at an example. Place the following elements in order of increasing ionization energy. Okay, so I'm going to look at increasing ionization energy. Okay, so let's look on our periodic table where each one of these are. I've got Ca, I've got As, I have nitrogen, I have Fe, I have CS, and I have fluorine. Okay, and so it's asking me to put these in order of increasing ionization energy. What do I know about ionization energy? Ionization energy increases as I go from left to right on the periodic table, and it increases as I go from bottom to top. Okay, so if I was to look at this on the periodic table, the one clear over on the left-hand side has the lowest ionization energy. And the one on the right-hand side has the highest ionization energy. So which one has the lowest? Remember, I'm going to follow these trends. So it's going to go cesium, calcium, iron, arsenic, nitrogen, fluorine. So it's going to go cesium, calcium, iron, arsenic, nitrogen, and fluorine. Okay, so we're going to compare these. Which one has higher ionization energy? Arsenic or nitrogen? Nitrogen does. Which one has highest ionization energy? Cesium or calcium? Cesium or calcium has higher ionization energy than cesium does. So we can look at the periodic table and come up with these trends. Let's do another example. In this time, it's asking, place the elements in order of increasing atomic size. Okay, so we're looking for atomic size. I have calcium. We have arsenic. We have nitrogen. I have iron. I have cesium. And I have fluorine. And I'm putting these in order of increasing atomic size. Atomic size. Well, what do we know about atomic size? Atomic size increases when we go from top to bottom. Why is that? We're adding electrons, right? Each period we add another quantum energy level. We're adding another row of electrons on there. We also increase atomic size as we go from right to left. Okay, so we're going to increase that atomic size. So let's look at putting these in order of increasing atomic size. It would go fluorine, nitrogen, arsenic, iron, calcium, cesium. What is the smallest element? That would be fluorine, nitrogen, arsenic, iron, calcium, and cesium. So what's interesting about this is, this was the exact same problem we did before, but they're in the reverse. So when we look at them and we're comparing them, metallic character and atomic size are the same. Right? We can compare them one-on-one. But when we look at ionization energy is actually the opposite of metallic character and atomic size. So if you look back at the previous slide we did, it's just the reverse order. Well, I hope this was very instrumental with this particular unit. I hope it gave you more of an understanding on how to do orbital diagrams, electron configurations, how we get those noble gas configurations, and also I hope it helped you with the periodic trends. So you can determine what is metallic character, atomic size, and ionization energy. If you have any questions about any of these problems or so forth when you're working through them on your homework, please don't hesitate. If you should have any questions about any of this unit's topics or anything, if you have a question about a particular question or something, please don't hesitate to send me an email and ask me a question about it. Take care.